I'm not sure if it's fortunately or unfortunately, of course, the diversity discussion also starts with just a few of the axioms, but I'll try to go to algorithms as soon as possible. Okay, and of course, first the story is about putting movies on a plane. So again, if we have Superman, Batman, Woody Allen, and Shrek, and if we have preferences like this, then if I can only put 2 movies on the planes, which ones do I pick? And here it would be sort of obvious that you need to pick Batman, Woody Allen, because that makes everyone happy. And if they can only, if each person would only watch 1 movie, that would be the perfect solution. And of course, if you used K-Borda, then you get somehow a silly result because Batman and Shrek. If you used Borda, Borda-Chamberlain Courant, and I will actually remind you of this definition a few times. Then, in fact, the score of Batman and Shrek is here 0, 1, 2, 3, plus 2, plus 3, plus 2, so it's 10 points. For Batman and Superman, it's even worse because it's 3 plus 1 plus 3 plus 1. But for the actual result, it's 12 points because everyone gets their pick. Okay. So recollection. So essentially, the whole part on diversity is on Chamberlain Courant. That's why I want to make sure we're absolutely clear what the rule is. So approval-based Chamberlain Courant means cover as many voters as possible, which means that, for example, the score of the committee orange-pink. So everyone who approves either orange or pink is covered. Our score is 3. 3 guys were covered. Red and green, just 2. Red and orange, 4. Okay? So I guess we're past the morning session. Now it's already afternoon, so of course it's no longer early in the day, which means you should be more active. Which means I would like you to say, yay, we understand.
We understand.
Yes. So actually, once I succeeded in my teaching in Poland, when I said, I gave some proof, and then there was this silence, so I said, okay, now on 1 to 3, everyone says, yes, we understand, please teach us more, master. Once they actually went down to master. Usually they skip that. It was a great day. Okay. So this is approval-based Chamberlain Courant. If we switch to Borda-based, sometimes I will write beta for Borda, sometimes I will write Borda for no good reason. So here we also want to cover as many voters as highly as possible. So if we have orange and pink, then that's 4 plus 3 plus 3 plus 4 plus 4. So again, in every vote, whenever orange is better than pink, it's orange. Whenever it's pink better than orange, it's pink. If we go for red, green, we have red, green, scored 13. If we get for red and pink, this is actually the best result you can get here. You have red and pink. Okay, so this is the rule. This is the rule that we somehow believe is good for diversity. And we want to show, so first we want to show it's good for diversity, and then we will actually want to compute it. Because the moment you see cover, a well-trained computer scientist thinks NP complete. Okay, but first the intuition. In individual excellence or shortlisting, we're looking for best candidates. Here we want diverse. So we have the same two-dimensional experiment. So if you look for K-Borda, this is, you get this center. If you compute Chamberlain Courant, you have this nicely spread set. So diversity is somehow covering the whole area. So everyone can find someone nearby who is good. So if you think of this in terms of movies, everyone can find good enough movie. Okay, so alone, each committee member possibly does not shine, but taken together, they're somehow satisfying everyone. Okay? And this is essentially like facility location problems, if you're familiar with that. So, but if you're not, then it's not going to help you. Okay, and this is actually a new set of pictures. that we will be actually using throughout the following discussion. So here, if we go back, we had this time the distribution here is a uniform disk, and we're choosing candidates and voters from this disk, here as well. And here we computed the winners. Here we computed the winners. In these pictures, this was the uniform disk distribution, and we put 10,000 elections together on top of each other, and we somehow created a histogram. So the darker a point, the more winners landed in this area. So essentially everyone landed more or less in the center, and there's just a small area which is more shady. Whereas, according to Chamberlain-Courant, this is mostly uniform on this disk, except that here you have this cross. This cross is here. You can see that just slightly on the edge, we're not choosing anyone. For some reason that you would have never suspected in the rule, Chamberlain-Courant rule somehow is favorable to extremists. So a bit more extremists are elected. But if you're kind of extremist but not too extreme, then it's a bit unfavorable. And then in the center, it's more or less equal. So this is actually, I don't yet know how to explain this behavior of Chamberlain-Courant, but we keep observing it in various experiments. So you would have never thought that somehow this rule is slightly supporting extremists, but well, what can you do? We don't have much better ones.
It looks like it is waving. So since you have nothing on the very edge, you
right.
have higher density.
Yeah, that's so of course that's true that since the voters who are here, they cannot get enough support, so they're somehow but then they band together here, and this means that these voters kind of don't get support from the area as well. So it's explainable in terms of, I can look at the distribution and see that this is the case. But if I did not see the distribution, then I wouldn't know how to realize that this will happen. That's what I mean. Okay, if instead of the disk you get a Gaussian distribution, then Borda is even more central, and Chamberlain-Courant is again kind of the same thing, because as you can see there's higher density here and slightly lower here, but it's kind of following that. If we have 4 Gaussians, again, Borda chooses a lowest density area somehow, but in the center, and Chamberlain-Courant copies the original distribution. There's a number of applications for this Chamberlain-Courant rule, such as the facility location problem, which simply says you have possible locations where to put, I don't know, bus stops, and so that everyone gets a bus stop nearby, or deciding which products to produce or which products to advertise. So this is actually one of my favorite examples. So if you're running, say if you're running a bookstore, if for some reason you just woke up and it turned out that you own Amazon.com, and you have to decide which books to, so when a user first logs in, he sees like 6 products, say. If all you show is Harry Potter 1, Harry Potter 2, Harry Potter 3, down to 6, which might be a bestseller at some point, and you're looking for a book on how to fix your car, or essentially how to make your life better, then maybe you realize, okay, this is not a store for me. But if there's a diverse set then of advertisements that somehow everyone is happy with, then maybe they realize, okay, there's lots of things I better look inside. So there's some applications. So let's try to go through the axioms relatively quickly, because there's not many proofs there. So there are actually 2 basic axioms that we realize are enough to explain somehow that Chamberlain-Courant is a good rule. One of them is narrow top. It says that if we're looking for, say, in this case, a committee of size 2, and there are 2 guys that are always ranked on top, then these should be the winners. And indeed, in this particular example, Borda Chamberlain-Courant elects them. K-Borda does not, because somehow K-Borda thinks that the red and pink ladies, which are somehow never on top but highly ranked, they're better, because the orange is great, terrible, and blue, great, terrible. Orange is, and the red and pink are okay, 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 okay. So that's why K-Borda, it's one way of looking at it is that it's good for choosing excellent candidates, but in fact, it's also choosing somehow the average. So that's also something to remember. Okay, so K-Borda certainly fails narrow top. Strangely enough, SNTV, which is this plurality-based also satisfies a narrow top, right? Who still remembers what's SNTV? 1, 2, 3, 4. 1, 2, 3, 4, and so SNTV simply means giving 1 point for the first position, 0 points for the others, and we're choosing. So is it clear now? Okay. Was that an okay? Let's assume it is. So if we look at this narrow top property, it's relatively easy that these representation focused rules have it, because if your scoring function is I1 through IK, and it is simply dependent some gamma of I1, then clearly if there are guys who are on the top in every vote, if you can choose k guys so that each of them is top in some vote, then clearly this will maximize the score given by this function. So every representation focus is narrow top consistent, but there are some other rules that also have this feature. Because, and the reason why there are other rules is simply, this is a property that tells you something about very specific profiles. That only if there's at most k guys that are ranked on top, then it tells you to do something. But if there are no k guys on top, you can do anything. So that's why these rules are in, but some other nonsense is in as well. So in particular, SNTV and Chamberlain-Courant rules are here. Okay, so we had this non-crossing monotonicity, and we were characterizing essentially weakly separable rules as non-crossing monotone. So it's not going to be very surprising that Chamberlain-Courant fails it, but let's see why. So if we imagine an election and we focus on a particular vote, let's say we have a red committee with score X. We have a green committee with score X. And what happens now if we look from the perspective of the red committee and we improve the position of the orange guy? It's a non-crossing move because he will pass the blue guy who is not a member of the red committee. And when that happens, in fact, the score of the red committee does not change because their best member is still at the same position. But the score of the green committee increased to X plus 1 because its best representative improved its position by 1, right? So I really want more interaction. We can go actually in rounds. So I guess you say okay.
Yeah, okay, so now green wins.
Yes, exactly, yes. Yeah. And and we moved, the guy was in the green committee fine, but he was also in red committee, so red committee should have stayed winning. Okay, you are for the next question. Okay. But in fact, this means that the mistake that we did was that we were pushing someone who was not ranked high, who was not the best in the committee. But if we take top member monotonicity, so if the highest ranked member of the winning committee is moved forward, the committee still wins. Now this is actually satisfied. So the red committee gets X points. If the green committee also gets X points, if we now shift the pink lady, well, both of them get a point and they're both still winning. So is that clear?
Yes.
Yes. See, you are prepared. It's actually not easy to prove that this, it's easy to prove that all representation focused committees have this property. What is less trivial to show is that if we now, so here we had non-crossing monotonicity, top member monotonicity is actually something more. Because if you're non-crossing monotone, you definitely are top member monotone, but top member monotonicity doesn't imply non-crossing. So in fact, this picture of non-crossing of top member monotonicity is something like this. However, if we add narrow top, then clearly the intersection is exactly the top member, the representation focused rules. And of course, this is a harder thing to prove. It's not very hard, but it's, so if you spend enough time, you can prove it. There's no magic involved. But it turns out that among committee scoring rules, if a committee scoring rule is top member consistent and narrow top monotone, it has to be a representation focused rule. And we would claim that these must be exactly the rules that are good for diversity, Because clearly, if there is, like with narrow top, clearly if every member, every voter gets a committee member he ranks best, then clearly it's a nice diverse committee where everything is covered. Right? I guess it's your time.
Could you repeat that?
Sure. So we can say that if there's an election, voters V1 through Vn, and we can find a committee such that everyone is ranked first in every vote, such that in every vote, one member of the committee is ranked first, then we can certainly say that somehow every voter is covered, right? And we say that this is our notion of diversity, that everyone can find the best thing, okay? And another thing is that this top member monotonicity means that if we had a committee, say with members like this, and this voter felt he was covered by this committee, so essentially by the top guy, if the top guy even improves here, then of course the voter is even more covered. Do you still agree? Yeah. Okay, so these two axioms somehow specify our idea of diversity. And so this Chamberlain, Courant, and SNTV, and all the rules that only take the first position into account are somehow diverse. And our experiments confirm this as well. So we go into computer science and computing Chamberlain Courant. Okay, so first, finding a winning committee under approval. So we're looking at approval Chamberlain Courant because it's easier to show NP hardness proofs for approval, but it holds for both. Is NP hard? And you could say it follows because it's essentially a max cover problem or a set cover problem, but we will show it. So in the max cover problem, which is almost like our set cover, we get a set of elements. Yes?
In Chamberlain Courant, we take the first one, like for water, the best.
So in approval-based Chamberlain Courant, actually, when I show it to you, it will become clear. Okay, so this is an instance of, so I call it max cover rather than set cover like before, because here my goal is, let's say I have k equal to, I don't have, but say I'm allowed to choose two sets, and I want to cover as many elements as possible. So I'm asking, is it possible to cover this many items? So in fact, I could, in this reduction, I could use set cover and simply ask, can I cover all of them? Okay? Now I'm forming an approval Chamberlain Courant election, where for every voter, so every voter is an element here. So voter V1, V2 is 2, 3 is V3, okay? You know you will be asked next, so I guess you're paying attention. I'll take it for a, please don't do it ever again, but yes. Okay. Now, element 1 belongs to yellow set and to the blue set. So every set is a candidate in the election. And we're saying that element 1 approves of the sets that he belongs to. Okay? And we do it as follows. So for example, number 2 belongs to green, red, and blue, or maybe it's pink actually. So we have red, pink, or magenta, violet, I don't know, and green. Okay? So you see how we form the election? Okay. And now, if there is a solution, so k is the number of sets we can use, it's also the committee size. And if there is a solution that covers everyone, then of course there is a committee, which is exactly the same things, where every voter is satisfied. So this is a one-to-one relationship between the problems, right? So if I can cover everyone here by using k candidates, then I can cover every set and the other way around. Are you satisfied and happy?
Satisfied.
Satisfied only. Okay.
Max cover, we should have k as an input.
Yeah, of course, it is part of the input. Yes. But actually,
It will be a problem, of course.
huh?
Otherwise, it will be
Yeah, sure, of course. Okay, so a similar, yes?
So if our sets are of size 2, is it also going to be NP hard?
I doubt it, because it will be a matching problem then. So this is polynomial time solvable. But of course that would mean we have a really restricted election.
So here the answer is yes, but if the answer to this cover is no, then how would it look like in the election?
So if the answer was no to set cover, then I would not be able to find a committee of size of a given size, such that every voter approves of some member of this committee. Do you see? Yeah. Okay. So if we go to Borda Chamberlain Courant, essentially the same proof works, but you have to work a bit harder for it to kind of use ordinal preferences. Okay. So Chamberlain Courant is NP hard. So deciding if there's a committee with at least a given score is NP hard. What can you do if you have an NP hard problem? There's actually a whole spectrum of things that people try. So one of them is you can use somehow general solvers. So there's a whole branch of computer science with things like integer linear programming, quadratic programming, SAT solvers, whatever SAT solvers, modulo theories. So there's a whole area of computer science that creates extremely efficient heuristics that can solve NP-hard problems very, very quickly, provided that you express these problems in their language. So in particular, we can express Chamberlain Courant as an integer linear program, feed it into, say, a commercial solver, such as IBM's Cplex or Gurobi, or you can try to use GLPK, which is available for free, and it will actually give you a solution. And we'll see that this actually works. In fact, all these results of NP-hard elections that I was showing here, they were all computed using ILP solvers. There's a theory of parameterized algorithms. So I will explain what it is, but you can somehow hope that maybe for elections that are somehow special, maybe if there's only few candidates, or maybe if there's only few voters, or maybe if the committee is small, you can hope that maybe you can do something. So we'll explain that a bit. There is an idea of domain restrictions. So when we were discussing Gibbard-Satterthwaite theorem, we said everyone is allowed to cast any vote he or she likes. But there are many cases, there are many somehow restrictions that people introduced that make things easier. And on some of them, you actually get polynomial time algorithms. You can try approximation, why not? And you can achieve quite high results. And of course, eventually you can run heuristics. So actually, okay, what is the difference between a heuristic and an approximation algorithm?
Sometimes heuristic gives infeasible result.
Yes, but a very amusing answer I got to this question was, well, I won't say from whom, but
in this case, every result is feasible.
yeah. So essentially, the answer I got, an approximation algorithm is a heuristic about which you can prove something. So if you can prove that it gives a certain level of satisfaction, then it's an approximation algorithm. Otherwise, it's just a heuristic. Okay. As we said, we can formulate, so we'll be using approval Chamberlain Courant here because, I mean, we're jumping between approval and Borda, whichever is easier for a particular proof. We can express it as an integer linear program. So just, I guess you are the next in line, the last person on that. So have you seen integer linear programs before? Okay, then this is an exciting moment of learning new material, just like for the last many hours. Okay. So, an integer linear program is simply a function to maximize, or minimize, in this case to maximize, and a number of constraints. Okay? So, linear constraints. So we're introducing two types of variables. So if you haven't seen these things, then I will spend here quite a while, because this is actually an extremely useful concept. So we will have variables that I call xj, and xj I'm intending that this means is the jth candidate in the committee. So I require that the variable xj is either 0 or 1. So this is a linear program because all the constraints and goal functions are linear functions of the variables. This is an integer linear program because I require my variables to be integer. And here by saying xj is in 0, 1, I'm essentially saying that somewhere on the side there is a constraint saying that for each xj we have xj less than equal 0, 1, greater than equal than 0. So we're simply adding this constraint to the program. Okay? So are you willing to be my victim for this slide?
Yeah,
Sure. So okay, so it's clear we have variables, we put them between 0 and 1, but since they're integers, they have to be either 0 or 1. Okay? So the meaning of variable xj is simply it will be 1 if a candidate with number j is in the committee, and it will be 0 otherwise. I will also have variable yi, which says, is the ith voter satisfied? And a voter is satisfied if there's a candidate in the committee that he approves. Okay? Okay. And now my goal function is to maximize the sum of the yi functions. So if I ensure that yi is truly what I intended to be, so it's 1 if the voter is satisfied and 0 if he's not satisfied, then clearly by maximizing this sum, I'm simply maximizing the satisfaction from the committee. Agreed? Yeah. Okay. And next I have constraints. My first constraint is if I sum over the candidates, then the sum of the variable xj has to be exactly k. Since xj will be either 0 or 1, and it's indicating whether a guy is in the committee or not. So by saying k, I'm simply saying for k candidates, the value xj has to be 1. For everyone else, it has to be 0. Okay? And the final constraint, I have it for every voter. I'm introducing a variable, introducing a constraint that describes if he is satisfied. So I put here yi on the left side. And here I'm summing over candidates that are approved by the ith voter. So if the value of yi is 0, the sum here certainly cannot be lower than 0. So if the value of yi is 0, this constraint is definitely satisfied. Right?
Yeah.
But yi can be 1 only in the case if among the variables that I'm summing up here, there's at least one which has value 1. So if this voter approves of 3 candidates, this sum will be equal to 3, but yi will only have value 1 because I have this constraint. Okay, so this constraint ensures that if a voter is not satisfied, he will have yi equal to 0. But if he is satisfied, then yi will be either 0 or 1. But I wanted yi to be 1 when he is satisfied. And the fact that we're maximizing the sum of yi's actually ensures that whenever possible, the variable yi will be set to 1 here. Right? So I can write such a linear program. I can take say off-the-shelf commercial solver of these things. I can feed it there, and the output I can read off the committee from variables xj. And this is unbelievably fast. So if you think about it, for the Chamberlain-Courant rule, if we take, say, 100 candidates, 100 voters, committee size 10, so 100 candidates, 100 voters, committee size 10. If we were trying to use a brute force algorithm that would simply try all committees, we would have something on the order of 100 to the power of 10 options to try. An ILP solver fed with this kind of data solves it below a second. It takes below 1 second to solve an instance of an NP-hard problem like this. This is why sometimes people say NP is the new P. This is not exactly true because there are still examples of NP-hard problems for which ILP solvers fail miserably. But for practical instances of elections, it's unbelievably fast to solve them using ILP solvers. So that's why I showed you a picture where we had 10,000 elections computed using Chamberlain Courant put together. The reason we could solve 10,000, 100 by 100, it was even 200 by 200 there, I think, NP-hard problems of solving Chamberlain Courant was because, because Cplex and ILP solvers or Gurobi do such magic, and because we had 100 cores to use. But okay.
Did anyone try to reduce the number of variables?
I don't think we really have, because at least for Chamberlain Courant, this is actually already so fast that there was never a need. There are other rules for which there might be some benefit in improving the programs, but not for Chamberlain Courant. Okay, so this was actually pretty darn practical way of solving Chamberlain Courant. The next attempt will be through fixed parameter tractable algorithms. And again, this is a notion from computer science that's addressing the problem of NP hardness. You can have probably whole course on FPT algorithms. I will just tell you the most basic things. And in fact, this lecture maybe is not the best advertisement for FPT, because actually our algorithms are not too smart here, at least most of them. But it's actually a very interesting theory of how you can somehow find easiness among hard problems. So if we have an exponential running time algorithm, the running time is expressed as some input size n. It will be, for example, some exponential function times polynomial of n. This is sometimes described with O big star or O star of 2 to the power of n. So the notation big O is ignoring somehow constant coefficients. The notation O star is ignoring polynomial time coefficients. Okay, so if we have an algorithm with an exponential running time, then what can we do? Well, and parameterized complexity theory observed that maybe our data actually has some parameter. There's something special about our data that could be quantified. So in case of our election problems, maybe this is the number of voters, which hopefully would be small, or number of candidates that hopefully would be small, or the committee size, or some feature of the input that hopefully can be small. And if we can express the running time of the algorithm as a function of the parameter, which can be exponential, times polynomial of the rest, then we claim that this is an FPT algorithm. Okay? So I need a new victim. It is you this time. So is it clear? Yeah. So the idea is that when you have an NP-hard problem, there's a geometric explosion of hardness of the whole problem. But if you can show that it's FPT, maybe the explosion is only small in the parameter. So if the parameter is within your reach, then you can solve it, but the rest is polynomial time. Okay? And as this parameterized complexity theory actually has a whole theory of hardness as well. So FPT is the class of easiness of parameterized problems. Then you have W1 hardness, which is a bit like NP hardness. Then you have W2 hardness, which is even harder, but why would you care? And because it's still hard. Then there is a class XP, which apparently has even harder problems, but it's a bit silly because, it at least feels a bit silly because XP are problems that are solvable in polynomial time, assuming that the parameter is constant. And you can wonder, well, where's the difference compared to FPT? So the next slide shows the difference. So if we have a running time of an algorithm, which is let's say exponential function or non-polynomial function of the parameter, times a polynomial factor of the input size, then this is FPT. On the other hand, if all you can say is the problem is solvable in polynomial time, assuming the parameter is a constant, so if you assume k to be a constant, this is polynomial. But this is not a function only of k, but a function of both n and k. So this is FPT, and this is XP. Is it clear? Yes. Okay, very good. Of course, if someone is not my victim, they can ask questions as well. Okay, so this is this kind of the shortest possible introduction to the parameterized complexity. And if we try to apply this parametric complexity to Chamberlain courant, it turns out that if we have few candidates, so it means that if we're somehow taking the number of candidates as a parameter, then there's a simple brute force algorithm. And if there's few voters, there's also a simple brute force algorithm. So I will actually explain these algorithms on the next slide, again in the approval setting. Because the situation is as follows. So we have approval-based Chamberlain courant election. I will ignore things that are written here because all I want is actually, I'll ignore most of them. So of course we have NP hardness which we have shown. It turns out we have W2 hardness for the committee size. This is actually extremely disappointing because the committee size is the only parameter that would truly be small in these elections in realistic settings. Unfortunately, we get hardness then. There's also some approximation which I will talk about later. But we can get FPT algorithms for parameters number of candidates and number of voters. So again, this is somehow poor advertisement for that I will show for FPT because I will show kind of really silly algorithms. There's much more complicated theory and in some settings they're extremely useful, just not here. If you take the parameter to be number of candidates, then you can simply brute force all possible committees. If you have few candidates, then the number of committees is m to the power of k. But of course the committee size has to be smaller or equal to the number of candidates, which is just m to the power of m. So you can brute force all m to the power of m committees, multiplied by the polynomial time of evaluating a committee, and you get an FPT running time. Okay? Are you still satisfied? Yeah. I see you see what's coming. Okay. On the other hand, if we move to the parameter number of voters, or here I wrote number of agents, voters, the same thing. The algorithm is still a relatively simple brute force, and it works as follows. First, partition the agents into at most k plus 1 groups. K is smaller than n, so here's guess, so essentially as if you were making non-deterministic guess. But remember, you definitely have k less than equal n, the number of voters. And your each guess could be work as follows. I'm looking at voter V1, and I'm choosing one of up to k numbers, which is less than n for him. Then the same for V2, the same for V3, the same, and they're put in groups. Okay? So I've partitioned them into groups, right? I could have done it, right? And the complexity of doing this is in the worst case, and it's something like k to the power of n, but this can be bounded by n to the power of n. Because certainly if I had committee size n, I would simply give everyone their best choice. Okay? So I'm still in the FPT world. And are you still with me? No? Okay. So let's ask the other question. Do you know what I'm trying to do?
I lose your way when we talk about the difference between FPT and XP.
Okay.
I don't understand the difference between
Sure.
FPT and XP.
Let's go back. So the definition of FPT is as follows. You have to have essentially whatever exponential or non-polynomial behavior has to be limited to a factor that depends on the parameter only. So you can have 2 to the power of k times n, this is fine, but you cannot have n to the power of k, because here the exponential blow up depends on both n and k. But here it depends on k only.
Is this some classification of the problems?
Of what problems?
More general.
Yeah, of course.
Some other examples maybe.
Okay. Let's.
Because if we fix k, both are polynomial.
Okay, let's.
If we bound k.
Yeah. Oh, because FPT is a subset of XP. Okay, but let's. So let me show you a non-trivial example of an FPT problem that has nothing to do with elections. So it will be vertex cover. Okay, vertex cover. Okay, we're given a graph G with vertices and edges. We have some number K. So we have some graph. Okay, whatever, somehow connected here. Okay, like this. Okay, we have a graph. Now, this you have to trust me, vertex cover is NP hard. It's even NP complete. So deciding if I can choose up to K vertices is an NP, so that every edge is covered, is an NP complete problem. But now I can show you an algorithm that will have running time more or less 2 to the power of K times some polynomial of the size of the graph. Okay? And my algorithm is as follows. I choose whichever edge, doesn't matter. I choose whatever edge, and now I have two choices. I can, because I have to cover this edge, and I can either cover it with one vertex or the other. So I have two choices. So I make a choice, I cover it with this vertex. Let's say, let's give them names. Okay, so I have a search tree that I started with this edge, and I can either cover, use vertex 2 or use vertex 3. I used vertex 2. So in this way, this is covered, but actually every single edge that is touching this vertex is covered as well. Okay, so they're all covered. Now I choose another non-covered edge, for example this one, and I have a choice, either 4 or 6. Let's say I choose 6. Okay, I choose 6, so I had the choice of 4 or 6. And this makes more edges covered. And now I have a choice of, for example, I choose this edge. I have a choice between 5 and 4. I chose 6, so okay, so 5 and 4. Let's say I choose 5. If I choose 5, these get covered. And eventually I have the final edge, and I will choose, for example, 1, and I will cover this, okay? So of course, I will only, so I have this search tree that I can go only K levels deep, because I can use only K vertices. So if I ever end up in a situation that I went K levels deep and I still haven't covered all the edges, that means obviously I failed. So I have to backtrack and try another option. But also, another obvious thing is that this is a binary tree. At every level, I have two choices, and so on. And this tree will have height of K. So at the end, I will explore at most 2 to the power of K possibilities, right? So this is an FPT algorithm for the vertex cover problem. Because it's only working, okay, it's FPT algorithm for the vertex cover problem under the assumption that K is my parameter. Okay, so I chose K to be my parameter. I showed an algorithm that runs in time 2 to the power of K times the size of the graph, some polynomial of it. So this is an FPT algorithm. I could, of course, give a much dumber algorithm, which is an XP algorithm. I could simply say, try every combination of up to K vertices. And then the running time would, of course, have to be n to the power of K times the size of the graph. Because for each, so I have n vertices to choose from for the first, then n minus 1 for the next one, and so on. So I could try all combinations like that. And this would be an XP algorithm for the vertex cover. Whereas what I showed here is an FPT algorithm for vertex cover. So is it now clearer?
The difference between this average is yes, but the exact.
Okay, the exact definition. Sure. So if we go even more back, the exact definition of an FPT algorithm is that the running time has to be expressible as a function of the parameter times a polynomial of the size. So this function can only depend on the non-polynomial part can only depend on k. This is the actual definition. Whereas for XP, the actual definition is that problem solvable in polynomial time, assuming the parameter is constant. So again, if we look at these two examples, this is polynomial time for constant parameter, this is 2. But that's fine because FPT is a subset of XP. But if you look at this function, it cannot be expressed in turn as some, so you cannot have f on.
One part depends only on k, and another part depends only on n.
Yes, so the other part depends only. The other part depends on k as well, because somehow we would say n is always bigger than k, because n is the size of everything, and k is somehow a size of something within. Okay, so is the difference now clearer?
So we have supposed to be fast.
So
FPT is supposed to be fast.
so in most cases, yes. Of course, you could imagine a situation where it's the other way around. In the same way as you could imagine a polynomial time algorithm like n to the 1000 will be slower than an exponential algorithm 2 to the power or 1.00001 to the power of n. So eventually, of course, the exponential will be worse. But so in general, FPT is better, but not always.
What if you have 2 times k multiplied by n times k?
2 times k.
And n times k.
So
you say that this part with n can depend on k.
do you say like this?
No.
So
2
power k.
in power k.
Yes. So 2 to the power of k.
2 power k and n power k.
Okay, this is still XP because you still have this element which is not allowed.
You said that this part can depend on n and k also.
Yes, but but polynomially. So you could have n to the second power times k to the 7. That would be okay. Of course, you could also move this to be together. But the thing is that it can depend on both n and k, but polynomially and not arbitrarily. Whereas the part which has only parameter can depend arbitrarily, in particular exponentially, on k. Okay? Are we acceptably better? Okay. So moving on. So back, we have number of candidates as the parameter, and then if we try all committees, this will be n to the power of k choices, but k, the committee size. So here m is the parameter now, because it's number of candidates, the parameter. K is the committee size, but of course committee size has to be no larger than the number of candidates. So it is actually m to the power of k is smaller than m to the power of m, which is a function of the parameter only. So if we just brute force like this, we have a trivial FPT algorithm. So in this case, FPT is not really helping much. Okay? If we go on to voters, now our parameter is n, the number of voters, which I called agents here. And now we first partition agents into at most k plus 1 groups. So for each of the n voters, I have to make one of k plus 1 choices. Right? Because I'm partitioning into k plus 1 groups. So for each voter, I have to choose which group he belongs to. So the complexity of this step is k plus 1 to the power of n. Because for the first voter, I have k plus 1 choices, times k plus 1 of the next one, times k plus 1, and so on. But the committee size is definitely no larger than n. Because if I have committee size larger than n, I simply give everyone someone they approve of, and we're all happy and we can live ever after. So the complexity of this step is essentially n to the power of n. Okay, so I get the partition. Now, for all but the last group, find a commonly approved candidate. Okay, I can do it. So in this group, I found yellow. In this group, I found red. And this is the last group where I found no one. So of course, if I guessed a partition where it was impossible to find commonly approved candidates, I would simply say, okay, too bad, I was not lucky. But if I get a partition that satisfies this, then I know that the guys from these groups, they get yellow as the winner, they get red as the winner, and this is my winning committee. And this gives me, again, a trivial FPT algorithm. So if I had really few voters, I could use this algorithm in practice. In most cases, it is simply a classification toy. So this means I have an FPT, and maybe someone could actually do some research and find much better FPT algorithms here for these parameters, but this was never done so far. Yep.
What's the point of k plus 1?
Because I need the last group without a representative. Because, because maybe there is no committee that satisfies everyone. So I have to account for that. Okay? So I'm choosing a committee of size k. But it might be that the best committee that ever exists at all does not cover every voter. So I need to I need the last group, the k plus 1 group, for voters who don't get a representative, who don't get anyone they approve.
Okay, you're maximizing this.
Yeah, yes.
Will such thing work? We just choose a subset of voters and union their approval sets.
Union or
subset of size k.
But union or intersect? So tell me again.
Union, I think.
So tell me again, what's your proposal?
I choose some subset. I enumerate all subsets.
Sure.
I choose some subset of voters. I take union of their approval sets. And I take some subset of k of this union. And this means that I satisfied the whole set of a.
Actually, it's not exactly that, because if you take, so I think you want to guess a group of voters so that all of them need to be satisfied, right? So if you guess them, that's fine, that's okay. And then if you take union of their approved candidates, if you take a committee from that set, you may skip someone, yeah.
And if I take intersection, then I can miss.
If you take intersection, then we're essentially back to more or less this algorithm, where you first guess the guys who will be satisfied and those who will not be satisfied, and then you can iteratively guess subgroups that. Yes?
Why do we have yellow but not red in V6?
Because we chose V6 to be in the group with V3 and V1, and yellow is their common approved candidate.
That's our just...
Well, so we have to guess these partitions. So of course we would also try a partition where V6 would be in the group with V5 and V2, and then he would have red. So these would be two equally good solutions. Okay. The next approach to solving Chamberlain Courant is by considering partial preferences. So I guess you are my victim now. I'm sure you're happy. So here the problem is that, so we have seen that we can use ILP, and this actually works like magic in most cases. We can try to use FPT. In this case, it actually doesn't work, or maybe we need more research. The third approach is maybe actually people are nice, and the way they vote actually makes sense, and it's easier to work with such preferences. There are several ways in which preferences can be restricted. One is single-peaked preferences, which are the political left-right spectrum. And the idea is as follows. So imagine that we can somehow order the candidates on a line from somehow extreme left to extreme right. Okay? in many political systems, people believe this is possible. And now, if we assume that every preference order comes to be from the following process. We choose the top-ranked candidate, and now the only candidate that we can add to the preference order after her has to extend this to be an interval on this is called societal axis. So here the next one is orange, it's fine. The next one could be either blue or red. In this case it's blue. The next one could be pink or red. In this case it's pink, and the next one has to be red. Okay, so these are single peak preferences. Everything fine. Okay. And it turns out that you can compute Chamberlain Courant in polynomial time via a simple dynamic programming algorithm if preferences are single peaked. There is a generalization of single peakedness called single peakedness on a tree. If the societal axis is a tree rather than a simple axis, they say, I wonder what they do. Nice. There's a button that says scare the presenter. If we have single peaked on a tree, then again we have an election. Let's say we start with the red guy, and then we again maintain continuity. So blue is okay. Now we have a choice of green and pink. We go with green, now pink and orange, and so on. So in principle, Chamberlain Courant for any tree is probably not polynomial time solvable for single peaked on a tree, but if the tree maybe has somehow nice structure, then it can be done. So still happy, right? Okay, another nice version of single peaked on a tree is single peaked on a circle, or the author was very happy with it because he named it Spock, and he somehow thought that it's really nice for somehow a movie series for Star Trek. And these are some of preferences for choosing a meeting time when you're in different time zones, because all you have is a cycle like here. So again, if you choose, you're supposed to choose your top guy, and then you have a choice of either orange or pink. You go orange, then pink, then say blue, like this. So again, easy enough. Okay, so fun times come. Because for this we will actually have algorithm. Not very detailed, but still an algorithm. There's something called single crossing preferences. They somehow arise in tax-related contexts. And single crossing preferences say that if you have an election like this, and if you take two candidates, such as red and orange, then they will only cross once. So if you can order the voters in such a way that it's red, red, and then orange, orange, orange. If you look at another pair, like green and pink, it's green, 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 then pink, pink. But it can never swap back. Okay, that's the definition. Still happy. Okay, and there's a whole bunch of papers that deal with Chamberlain Courant under these various assumptions. In particular, we will look at single crossing. Yep.
So this single crossing, is it the same single crossing property as for incentive computability or different mechanisms?
It probably comes from the same root. Whether it's exactly the same.
When you say tax-related issues, it was first shown this was required for taxing, such that the tax system is incentive compatible. Is this what you mean?
I have to admit that this is, and it's related to tax-related issues. This is something people always say when they say single crossingness, and most people, including myself, have not read the two original papers where it was introduced. So I believe that what was done is that in those papers, the authors were somehow explaining that if for some people have some sort of rational preferences over how much tax they should pay, then these preferences will end up satisfying the single crossing. But I don't think it was, I'm not sure if it was about designing a tax system. It was more about voting or expressing preferences over things. But this is as much as I can tell. I think I know one person who read that paper, but maybe more. But okay. But at our level, this is just kind of definition of what profiles we're looking at. These are kind of, so do you think these profiles are realistic? You think yes? Yes. Maybe someone thinks they're complete nonsense. What's your opinion? It's not enough to just say yes.
It's okay.
So actually, most people, when they see single crossing, they think it's absolutely unintuitive. Why would a profile satisfy this property? I see you guys have more to do with mathematics than most, yes?
So these 2D diagrams, wouldn't they also have?
They're not exactly single crossing, but if we move to the 1D world, this is so if we imagine a one-dimensional world, so we have candidates A, B, C, D, and E, and if if I put a voter, say if I put a voter here, like in our 2D spectrum, I would say this voter, V, he's closest to C, so he likes C best. Then B is actually closer than D, so he likes then B, then D, and then between E, A is closer, so A and E. Okay? So if we form preferences like this, then first of all, it's actually single-peaked, but it's also single-crossing. And the reason why it's single-crossing is that if you look at some pair of candidates, so for example, if you look at C and D, then there's a line exactly halfway between them. And as you consider voters moving from left to right, every voter on this side will think C is better than D. Every voter on this side will think that D is better than C. And that's why it's single crossing. So in this case, it's both single peaked and single crossing, but at least there are some situations where single crossingness actually arises in nature. Okay.
We learned that this property holds for one pair.
Say again?
It holds for one pair of candidates.
It has to hold for every pair of candidates.
And here it doesn't hold for pink and blue.
So it's pink, 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 blue. Yeah. Yes. Okay. So we can now give an idea of a polynomial time algorithm for Chamberlain Courant with single crossing preferences. I will not make it very formal, but it will be just kind of idea how this works. So first, so this is the order in which the election is single crossing, and we take the top preference to be somehow special. This will be our guiding force, so we are copying it and we're putting it on top. And then there's a nice feature. So you can ignore maybe what's written here, and I will just explain. So imagine that we're going to form the committee by moving somehow from left to right on this order of candidates, and by moving from top to bottom on the set of voters. Can I do it? Yes. So first I decide, somehow for some reason I decide I don't choose the red guy. But I will choose the orange guy. Okay? I'm choosing the orange guy. So far he is the only person in the committee. And so everyone has him as the representative. Okay? So I move one voter to the bottom. Do I want to add another committee member? Maybe not yet. So I move one voter to the bottom, and now I say, okay, do I want another committee member? I can only move in this direction. Actually, that's what I claim, but it will be clear soon. So I can add either green or pink or blue. I decide to add pink. And from this point on, of course, it only made sense for me to add someone who was in front of the red guy. So the choice was technically, sorry, in front of the orange guy. So I was choosing between really green and pink. I chose pink, and you can see that the moment I chose her, the guys represented by the orange guy are only on top, and here below, everyone prefers the green lady, the pink lady. Because before he was better than her, now she is better. By single crossing property, this doesn't change. Okay, I move down the voters immediately to the bottom because here I do nothing, and here I decide that the blue guy is in the committee, so I put him in, and in the end, if I choose a committee from whatever committee, it will always be that whoever I choose, who is the most leftmost guy will get the top block, then there will be the next block, and so on. They will always be in blocks. Are you willing to accept that?
Why we didn't choose the green lady?
I just showed it's just an example. But my point is that when I choose a committee, the sets where a given guy is the best among the committee will always be contiguous.
So again, dynamic programming.
Excuse me?
So again, dynamic programming.
Exactly, and that's exactly the solution. And when you know they're contiguous, you have a simple dynamic algorithm that computes the best committee. Because I will not give it in detail because simply I will not, unless you really, really want to. We can make vote. Who thinks that maybe not doing the DP is not the worst thing? Yeah, of course, I meant to confuse you.
Double negation.
Yes. Okay, do you know the story of double a joke about double negations? And there's a linguistics professor who's giving a really important lecture at a very important conference. It says, double negation is an extremely interesting thing. There are languages in which double negation means no. There are languages in which double negation means yes. There are languages in which double negation is not allowed. Interestingly, there's not a single language in which double positive means no. Someone says, yeah.
Yeah, in Russian it's yeah, of course.
Yeah, something like that, yes. Okay, this was not very funny. Okay, so essentially, is there someone who really wants to see this dynamic program? Luckily, no.
Can we go back a little bit?
Yes.
Why did you not choose the green lady?
Oh, it's no.
The third step.
This is just an example.
Yes, but how do we choose? What's the?
Okay, so let's see. So imagine. So what would happen if we chose green lady instead of pink lady? Is that your question?
CC is chamber and column
Yes.
for border scores.
So CC usually just, so in this case we're using border scores because in these slides, whenever I have ordinal preferences, it is border. If I have approval, it will be approval. Okay, so.
Why did we not choose green lady on the step 2?
Okay, so because I was simply showing, so my point was to simply show that you get these contiguous blocks. But if you chose orange, green, and blue, then what you would see, so here between orange, green, and blue, orange is best. Orange, green, and blue, green is actually better. So so it was orange, green, 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 blue. So it's still contiguous. So maybe I chose,
Which one is better?
so in this case, let's say this one would be, so 0, 1, 2, 3, so it's 3 plus 2, it's 5.
You don't have to compute.
But I mean, you did ask. I'm here to please.
We haven't shown algorithm, we just show the properties that this is continuous.
Yes. So no matter what committee you choose, it will always be contiguous, and that's why it's so easy to make a dynamic program.
So we can say that we should choose someone on the step only if single crossing happens on this step.
So essentially, we can only choose. We don't even have to really do it because we could make the dynamic program work without it. But of course, that's when it makes sense. So we could optimize the algorithm this way. Okay. And the next thing is approximation algorithms. And I guess we move to you with as the victim. Okay, the first approach is simple greedy approximation. It's called greedy Chamberlain Courant. And the way it works is it's a very simple algorithm with a very simple analysis. The analysis is very simple mostly because in the 70s, someone, Nemhauser and others, proved a remarkably strong theorem that we use here. But before we explain how this theorem helps us, here's the algorithm. So we have preference orders, and we're using Borda-based Chamberlain Courant rule. So we have election and committee size, and the algorithm is simply for I going from 1 to k, in each iteration pick a candidate that increases the score of the assignment the most. So in the first iteration here, I would choose the red guy because his Borda score is highest, and the amount of points he's giving me is 4 plus 2 plus 2 plus 1 plus 2 plus 4. Okay? In the next iteration, I would choose the green lady, but I only give her the additional points that she obtained, and so on. And this is guaranteed to have 1 minus 1 over E satisfaction, which is about 0.63 approximation ratio. And this is, as I wrote here, it's standard greedy optimization of monotone submodular set functions. So this is a classic result from Nemhauser and others. And what it says is that you have a monotone function, which means that if you have some set S and some element C, then a monotone function has to guarantee that value of this function of S union C is greater or equal than value of just S. So by adding things you cannot damage. And this is true for the Chamberlain Courant rule. As you put more and more items in the committee, maybe you don't help, but you certainly cannot hurt. So agreed? We have this feature. Yeah. And the function is also submodular. And let's say that we have two sets. A, which is a proper subset of B. And we have a committee a candidate C. Now, submodularity means the following thing. Let's say we have F. So A is a subset of B. So B is the larger set. So actually, let's start with A. If we take A union C, so we have added element C to a smaller set A. And we take the marginal contribution of this element A, of this element C. So this was the value we had before. This is the value after we added C. This has to be greater or equal than the same thing, but for committee B. Okay? So this means, so you can think of, let's say that our committee A is empty set. Now, if we added a green lady in this case, it would have given us a lot of points, right? The green lady would give a lot of points. But if we have a bigger committee already, then adding green lady gives us only this small amount. So essentially the marginal contribution for adding someone to a smaller set is greater than adding the same person to a larger set. And of course, this in terms of inclusion. Okay? Agreed? So, yeah, so this is the definition of submodularity. So this is monotone, and this is submodular. So, what Nemhauser and others have shown is that if you have a problem of finding a set of k items that maximizes some function, then simply doing it greedily step by step will definitely give you this 0.63% approximation. And this is a theorem from the late 70s. So essentially, whenever you have a submodular function, you're guaranteed that this simple, iterative, greedy process gives a good approximation. Yes?
What is E?
E is 2.78. But it's a good question given how many symbols I did not introduce. Okay. And the interesting thing is how this algorithm actually works on our 2D experiment. So of course, in the very first step, it chooses a candidate right in the center because that's the Borda winner. But in the next steps, it kind of nicely spreads around. And you can see that this actually has, if I decrease the size, increase the size, you can see that the rule is actually committee monotone. Because it's a greedy algorithm, it can only add, once it has added someone to the committee, it cannot take it away. Because the algorithm is somehow agnostic of the committee size. So we just stop it at some point and say this is our committee. Yeah.
What's the worst case where this is a tight bound?
I honestly don't know. I'm not sure. So it's not even clear that this is the tight bound. It's simply guaranteed that you will never be worse than 63% of the ratio. But in fact, maybe the true lower bound is 80%. Who knows?
And this bound 1 minus 1 divided by E is for general submodular?
Yes, for absolutely every monotone submodular function.
Can we estimate this bound for Borda scores?
So can we get this bound for Borda scores?
Yes.
I don't know, because we have a better algorithm. So we can obtain a much better result without using this. So I guess I just never bothered. But okay, and however, these are the pictures we have generated for Chamberlain Courant. If you run greedy Chamberlain Courant, you actually get very different pictures. So you have this aiming practice for when the distribution is Gaussian. So of course, in each of them, you can see how the Borda winner is always selected. But then if Borda winner is selected, then the guys right next to him are not. So the other ones are, and the next ones are not, and so on. So you can always have this wavy effect is much stronger here than in actual Chamberlain Courant. Yeah?
Shouldn't we maybe try different initialization?
Sure. So of course, yes. So indeed, that's true. That you could simply, for example, you could choose randomly the first guy, and then continue with the greedy.
You could do it with every guy.
Huh? Say again?
You could do it with every guy as the first guy,
Yes.
and then select the best one.
That's true. That's true. Maybe this would give a good result. In fact, so I haven't tried the exact solution you suggest, but we have tried a version of the greedy algorithm where instead of choosing the guy that contributes most, we somehow, there's a way to estimate which candidate will contribute most in the final committee. So it's using some game theoretic concepts such as bands of value that somehow try to predict that if we fill in the committee randomly, and I'm choosing the last person, what will be his contribution? And based on this principle, we get very much better results, at least for this setting. But indeed, if you play with the condition for choosing the guy, it's probably possible to achieve something better. But here, the niceness of this algorithm is that it's extremely simple. So, and unfortunately, the price for simplicity is that results on their own are actually quite good. So every specific, so if we move back, this looks like quite a good result. I mean, you see maybe a little bit of this in the center, that there's some space, but it still looks like a good committee. And if you compute the actual satisfaction, you will get something like, I don't know, probably 95% accuracy. But if you run it for 10,000 times, you see that there is clearly a bias. Okay. So what we decided to do was, okay, let's try to improve upon this algorithm. And what we designed is we called algorithm P. Again, my co-author came up with it, so maybe his name was Piotr as well, so I suspect there is some correlation, but he claims it's not true. Okay, the way this algorithm works, So by the way, this is again this will be a full analysis. So the way this algorithm works is that we're supposed to choose k winners, among m candidates to get, and we want the highest satisfaction or utility or whatever you call it. We're using Borda scores. So here's rank, which is the opposite of the Borda score. And first, we forget about the whole profile beyond rank x, where x is number of candidates times Lambert's W function of k divided by k. I suspect that probably none of you have heard of Lambert's W function. I have not heard of it either before I started working on this algorithm. It essentially came up from the analysis. So I will show you the definition soon, but for now you can think of WK as something that's a bit slower than logarithm. So we compute some point like this. We say everything behind this line is forbidden, we're just not looking there. And the algorithm simply says in the loop, keep picking the candidate that appears in the available part, the white part, of the profile most frequently. So if there are some candidates there, then we choose one of them that appears most frequently, and we're saying these voters are covered, and they're out of the game. We're then choosing someone who covers the rest, and yet someone, and of course someone will be left uncovered, but that's how the algorithm proceeds. Okay, so I guess it's your turn now. I guess you're free. So is the specification of the algorithm clear? Okay, so back.
So first you put this bound, and
yes.
That,
so
the most frequent.
Yeah, so I put this bound, and I'm saying I don't care about anything that happens in this part of the profile. Then I look at all the candidates that appear here, and I choose the candidate that appears here most frequently. In this case, it's the thing with big teeth. So I include it in the committee, and I say that everyone who ranked this thing in this part of the profile is now covered. So I remove these voters from consideration, and I'm left with smaller sets of voters, and I'm now looking who is most frequently here. So apparently the vampire is here, so I choose the vampire, and he covers these guys. And now let's say my committee size is 3, I still choose the Frankenstein, I get one more voter. I'm left with one unsatisfied voter, but what can I do? So this is the algorithm. Okay?
And the utility is in terms of...
Utility just means the score.
Well,
Borda score.
then it's strange that we choose just most frequent.
Yeah, so we're simply claiming that, so the intuition is that this area is so small because it's simply, so remember that WK is like logarithm. So if you take log k over k is a very small amount. So you take very few top preferences. So we're simply saying that all of them are as good.
So eventually we're picking up k winners.
Yes. So this is the k winners. This is the. Yeah.
Okay, but then we at some point move this line.
No. The line stays here forever. That's it.
But if like okay. So
That's. It is what?
If there are just less than k different guys in these stripes, then we pick up committed small size, but it's...
Yeah, and then we fill in with whatever. Okay.
How we generalize it for different scoring group?
You don't. It's geared for Borda, that's it. Borda Chamberlain current. Okay, so now let's, and the analysis shows that you actually, that the number of points that you can get is number of voters times number of candidates minus 1 times this thing. And this is actually, if I got a committee where everyone was ranked first, then they would have exactly this score, which means that what's left here is my approximation ratio. And this is actually pretty darn good, because if WK over K is so if WK is like logarithm, it means that the larger K is, the closer this is to 1. This means that, for example, for committees of size 100, I'm probably at 99% accuracy already. And in fact, I can get a PTAS, polynomial time approximation scheme, by simply saying that for a given approximation ratio, if k is not is kind of too small to give me that ratio already, I just brute force the solution. And if it's big enough, then well, the algorithm does it. Okay. So now
This should be obvious.
no, it's not obvious at all. It's nothing like obvious. I mean, I will actually show okay, it's not too hard, but it's not obvious at all. So maybe now the question is, do you want to see the proof of this approximation bound now, or do you want to see it after the break? So the question, who wants to see it now? 1, 2. Who wants to see it after the break? 1, 2, 3, 4.
After the break.
Well, there's supposed to be a break.
And I do.
Yes, and
Will be
excuse me?
our topic. The next topic will be.
So we can continue with this, at least to finish diversity. And then we will actually have a point of decision. We can either go into proportionality, or we can go back to what was done yesterday. But I guess there was a majority for taking the break now. So I can only tell you that the proof looks like this, and it's not so complicated, and we will explain it after the break.